Hello, it is I the dog. Please consider subscribing. Every subscription earns me one treat. Thank you.
Alright, welcome back to another video, and in this video we're going to be talking about the basics of derivatives. And to kick things off, we're just going to consider the definition. So if we think about a derivative, what we're really trying to express is the rate of change of a function at some specific point. And this is all going to stem from the point-slope form equation. And if we want to find the tangent line at some point A, which would correspond to the function at that value A, well, we can simply solve for what m is by taking the limit as x approaches a, and then we just have f of x minus f of a, and then in the denominator we have x minus a. So if the words are a little bit confusing, we can jump into an example. So let's say that our function is x squared, so we would say y is equal to x squared, and we want to find the tangent line to y at some point where x is equal to 2. We know that y is going to be equal to x squared, so that's going to be equal to 4. So if we use what we just had up here and plug that in down here, we can simply plug in the value of 2 for a for the limit. And then above our function, that's just going to be x squared minus f of a, which is going to be 4. Again, that's right here. And then in the denominator, we have x minus 2. Now we can expand this x squared minus 4 to simply look like this term here, and notice the x minus 2 in the numerator and the denominator cancel out. So this is simplified to the limit as x approaches 2 of the quantity x plus 2, and you could use your left hand and right hand limits to arrive at the same value and confirm that that limit does exist. So now we can plug that back in above, where now we can take the points in P and also plug those in for y1 and x1. So we just arrive at this here. And then by simple manipulation, we can say that y is equal to 4x minus 4. So that would be the tangent line at the point P that we had up here. And we don't have to have a specific point. We can kind of generalize this and say that we're going to let x2 be equal to x plus h, and x1 is going to be equal to x. So just some arbitrary value for h here. And then we can also say that y is equal to f of x, but we have the subscript I to denote the 1s and the 2s. And we can rewrite our equation that we introduced before with these corresponding x values to have f of x plus h minus f of x is equal to m. And then we have x plus h minus x. Notice here the x's will cancel out. And what we're left with is m being equal to this quantity here. And what we're going to do is actually take the limit as h approaches 0, so that we're left with this term here. And this is what is going to be equal to our derivative. So you could say that this is equal to f of x prime. That's one notation you'll see with this prime right here. You also might see the notations that look like this. So you have the derivative with respect to x of the function, or you might also see, so all of these three things mean the same. And if we consider what we just looked at above right here, for the case of x squared, you can see that y prime, which also is another notation you might see. So we can actually add that in here, so you might have y prime as well. And if we plug that in, so we have the limit as h goes to 0. So we have x plus h, that quantity squared, minus x squared divided by h. We can simply expand this term and we'll have some cancellations that occur. And that arrives us at this right here. So we have the limit as h goes to 0 of 2x plus h. But notice here we're taking the limit as h goes to 0, so this h falls off and we're just left with 2x as the answer to that limit. And then here, if we plug in x being equal to 2, we get that y prime is equal to 4. Notice here that this did not give us the function that we had above, but that's because we are defining m. Now if you notice, this value down here is 4, and what we found for m right here is also equal to 4. So we have matching values. And if we dive into this a little bit further, again, we have some more words. So the process of finding a derivative is called differentiation. And what it does is that it tells us this instantaneous rate of change for a function, but maybe in more easily digestible words, we're looking at how fast a function changes, and it's going to be visualized by the slope of the tangent line at some point. So that's all that a derivative is really telling us. Now we can say that a function is differentiable at some point a if the derivative exists at that point a, and this leads us into being able to say if we're able to do this at that point a, then f of x, or that original function, is continuous at that point A, which we'll see why that's important all throughout this course. But let's consider an example, and we're going to say that the function that we want to investigate is the absolute value of x, and we want to investigate that derivative at x equals 0. And this may seem straightforward, but let's look at the left-hand and right-hand limits. So the left-hand limit we have here, notice that we have the 0 with the minus sign. And from the previous video, we know that that will tend towards -1. But if we look at that limit from the right, it will go towards +1. So what we say is that the left-hand limit does not equal the right-hand limit. So you could say that this is divergent, or the limit does not exist. So we can write that in up here. And if the limit does not exist, well then we can't differentiate that function at that point. And this brings us into another kind of condition we'd like to have. So continuous is pretty cool, but having a smooth function is also pretty nice when we are looking at differentiation. So if you plot here the absolute value of x, it looks something like this. And while this function does look continuous, this smoothness right here kind of becomes an issue because it's not smooth if we zoom in right here. Now we can also have higher order derivatives. So you could take the derivative of some function, and then you just get 2 primes here. And it follows a similar procedure, except now with this f of x plus h, we throw on the first derivative here for both the x plus h and the x term. But again, you just take that limit as h goes to 0, and you'll get your result. And the notation gets a little bit weird once you get into higher order derivatives, because you might see this double prime here, but you might see the one that I hate, where you have a parentheses and then a 2. And there's a number of reasons why I don't like this. For one, it looks too close to f squared of x, which is not the same as the second derivative of x. And maybe if you're in the finance world, to you this parentheses with the 2 maps to -2. And again, you might get confused and say, okay, is f raised to the -2, is that equal to the second derivative? And again, the answer to that is no. So the notation that I kind of prefer is to just completely avoid these primes or this weird parenthesis number and simply use something that looks like this. And we can end the video with looking at power functions and derivatives. So we're going to consider the function y is equal to x raised to the n, and we want to find the derivative of y. So let's plug that in and see what we get. So if we plug that in to find the derivative, again we take that limit, and pretty quickly the math really starts mathin', because now we need to look at the binomial theorem. So if we have x plus h raised to the n, we can represent that as this awful term right here. And what we're going to do with that awful term, we're just going to expand it. But not all the way, we're just going to look at the terms for k equals 0 and then k equals 1. And then we just represent the rest of this term right here, simply by having k equals 2 in the summation. So now if we plug this result back into this equation here, and simply look at the numerator, what we get is that this x to the n and this minus x to the n, those are going to cancel each other out. And now what we're going to do, we're going to take this term, divide it by h. So we know that the h's from right here will cancel out. So now we can do the last step. So we're going to take the limit as h goes to 0 from what we just got right here. And notice here for the first term, there is no h, so nothing happens. But for all of this summation, we do have this h term, and as this goes to 0, this entire term will also go to 0. We're just left with that first term. So that's what we get here. And notice that this is the entire formula for the derivative. So we can plug that back in. So this is what our derivative is going to be. So now if we map this out, if we have some function, x to the n, we take the derivative of that. The resulting function is n times x to the n minus 1. And we can confirm that, again, just by going up to our previous example. Now in the next few videos, we're going to look at a lot of properties of derivatives because it's not always this simple. But if you learned anything new or useful, please like, comment, share, subscribe, and we'll see you in the next video. Thank you for watching.